So in this pictorial, we describe the design and implementation of a shape-changing artifact, and which is named deformTable. And the shape-changing artifacts refer to physical changes in material forms as inputs or outputs of computing. And the overarching goal of this pictorial is to share reflections on our process and to design a shape-changing artifact, and that could enable investigations of lived-with experiences of shape change and critical operations that emerge over time. So deformTable is highlighted by its counterfactual feature. It can rise up and down according to the weight of objects placed on top of it. So informed by the drift table and the table on table, we sort through a desired computational form to invite people to explore new and unknown appropriations through dynamic shape change. And we also paid attention to the refinements of the physical form of deformTable as a level of finish, fit, and independence of a research product. And we crafted and tested deformTable over 80 mouses. And we tested an early assembled prototype and to iterate the materiality, deformability, and temporality of deformTable. And framing the expressions of change also as inputs and outputs allowed us to explore shape change and temporality as a process of software program. So the input interface of a deformTable is its wooden top, and that can detect weights ranging from 20 grams to 5 kilograms. And the output surface is an elastic fabric and upholstered to the physical form of deformTable, and which emphasizes how the dynamic shape changes in 4. So ultimately, we small mass produced 5 sets of deformTable devices. And next, we will describe how we address the different challenges in attending to the dynamic physical form of deformTable. So initially, we used the 5-volt stepper motor and to actuate the desired mechanism. However, we found the initially desired mechanism deformed the fabric, and only after we slowed down the actuation speed. And we found it could not function reliably over time since the output torque was not sufficient. So to address this, and we tried another stepper motor, and that had more torque and overload capacity. And yet we found the driver would overheat after 10 minutes of use, and even when we placed the heatsink on the chip. And to address this friction, we explored a linear actuator and with an integrated potentiometer, and that can incorporate positional feedback. So next, we tested different load cells, and we wanted to be open or make the table capable of any possible encounters, and particularly in relation to the weight placed on it. Given this, we explored lower capacity load cells until we found a weight ranging that meet the requirements of foresee everyday encounters. So in the end, we calibrated the load cell and to a maximum of 5 kilograms, and that was more adaptable for deformTable as most daily items were less than 1 kilogram. So having explored computation, actuation, and form separately, and we needed to bring these together into a single functioning form. Thus we modeled and the early prototype, and so however the main challenge was how to design structure, and that could be assembled to upholster the fabric cover, and we designed a dismountable physical form to solve the problem. First, we upholstered the fabric around the surface, and we then screw connected the fabric form to the wooden base and the actuator of deformTable. And lastly, we unscrewed and connections on the dismountable structure. So we rendered the form of the prototype and to speculate on compositions of different materials. So after we have the initial model, and we decided to print all the parts out for testing, so many issues arose out of crafting the assembled form, and rather than planning it or out ahead of time. So for example, we found out our 3D printer could not print the digital parts, and that exceeded specific dimensions, and this created a remodeling of large parts into several smaller components. And we connected like all the circuit of the early prototype. And specifically, we connected the motor driver and the load cell to and programmed the Arduino Nano board. So informed by former design explorations of slow technology and material speculations, we tested the early prototype of deformTable by living with it and expressing it in our daily environments. And we wanted to derive first-hand insights, and that could help us refine the deformability and materiality of deformTable. So our early prototype had black fabric, and that discovered made it difficult to perceive the nuance changes on its surface. And the early prototype was also solid, making it difficult to play with the inherently soft dynamic shape changes. So we also found that the early table is not stable, when we place large pieces on top of it. So to address this problem, we mounted 3 supporting poles and to stabilize deformTable by manually drilling holes on the base of the early prototype. So accordingly, we redesigned the physical form and to enhance the potential for creative appropriations. And we purposefully designed the hollow space between the elastic fabric and also the material form, and which added an open-ended quality, leveraging the nature of the fabric to cultivate new and unknown appropriations over time. Assembling and refining the form also called for a level of experimentation and judgment, and to create a robust artifact and that could fit different households. And we translated this in part to designing deformTable, and such that it was both computational and non-computational artifact. So the aim of fabricating wooden parts was to enhance the simplicity of deformTable, and we decided to use solid wood to produce the top surface and base of deformTable, while keeping other parts as white-cornered plastic. So after we sending the 3D model to a factory, and the technician fabricated the top surface of deformTable and the technician also clamped the wooden base and to drill screw holes on its side. And we 3D printed all the plastic parts and CNC milled the wooden parts simultaneously. We also assembled the materials and also electronic parts into a set of shape-changing research products. So in this final assembly, we encountered a remaining challenge of how to smoothly upholster the elastic fabric and onto the hollow structure without any wrinkles or unwanted draping. So we found that we need to fabricate additional parts to assemble the fabric on its mountable structure in a consolidated fashion with the rest of the structure. And ultimately, we produced 5 sets of deformTable devices, and that we believe support creative appropriations in early settings over time. We deployed 5 sets of deformTable to 5 independent homes over 5 months in Metro Vancouver, Canada. So for this picture, and Sophie's son played with deformTable as his digital toy. And also Lydia played with deformTable and Jessie used the deformTable as a flower stand, and by placing her flower pot on its wooden surface. And Olivia decorated the deformTable with Christmas ornaments and to fit the Christmas theme of our living room. And also Daniel's cat Coconut played with the cat teaser and placed on the wooden surface of a and this video demonstrated how Coconut interacted with the shape-changing surface of deformTable.